Hello, this is Amos the STEM guy, also known as Amos the Math guy. Amos the STEM guy plus Amos the Math guy equals STEM excellence by God's grace. In this video series, we're going to be going through a book called Journey Through Genius, written by Dr. William Dunham. Now, I've written my own resource called Tools for Mastering Mathematics, which you can find in the on our website, as well as a math curriculum called Inspirational Mathematics 1, 2, and 3. Together, they're take you from basic counting all the way to calculus. So that's a little bit about my background. I'm a medical physicist as well as a math and science curriculum writer with a degree in chemistry from the University of Wisconsin in Superior. So let's look at the book that we're going to be studying. It's right here. It's called Journey Through Genius. So join us as we study the lives of Isaac Newton, Blaise Pascal, Leonard Euler. There are other chapters in this book, but we're going to focus our efforts now in the scientific revolution, which gave us physics and so on and so forth. So stay tuned for more books in this series. The last thing America needs is any talk about math being some sort of invention or like it has its ownership from some sort of ethnic group here or ethnic group there, and you need to decolonize math and all of that. We need to stop that in America. America is already behind in math. America is one of the worst industrialized countries in K-12 math performance and review. And now we're going to be introducing anything that would reduce the time to have excellence in mathematics. Do you know who the best in math are in the world? Most of the countries that are best in math, they're not actually necessarily from Europe. I mean, there are some countries in Europe that are very good in math, but we're talking about Shanghai and Japan and South Korea and Nigeria and Indonesia and Pakistan. And those are some of the best countries in the math in the world in terms of performance over time. Singapore is one of the best with elementary math. And so when we look at the state of affairs of math in America, what does America need to be doing right now for math? America literally needs to take this summer and say, everybody, come. We're not going to have a 3-month summer break like we've had before. Everybody's going to have to roll up their sleeves, and you guys are going to do some serious math over the 12 weeks of summer. Yeah, you can play, but you don't have to do science. You don't have to do extra social studies or history. I mean, you can if you want, but math, we need to brush up on our math. I mean, COVID pushed a lot of people back because of the lockdowns, right? So people are still trying to catch up in math. And then I'm hearing about school districts that are having conversations about decolonizing math. Do you know that one of the best mathematicians in the world, a man by the name of Srinivasa Ramanujan, from India, was self-taught? He didn't even have high school and college instructors initially. He taught himself math, and that's the thing about math. Math does not care about where you're from and what's your background. Math literally will give you tools. If you give math time, math will reward you accordingly in terms of just how proficient you become in the subject. And so what I'm going to do is I'm going to talk to you about Journey Through Genius. That's part of what we're going to do in this series. We're going to learn from the best mathematicians the world has ever known. So this is Amos the Math guy and Amos the STEM guy, which equals STEM excellence by God's grace. And what I'm going to do is we're going through the history of math, and we're going to pull out lessons from the best. These are not people that people think are the best. No. These are the best. Isaac Newton, Leonard Euler, Carl Friedrich Gauss, Blaise Pascal, René Descartes. These are exceptional mathematicians. How were they educated? Now, I grew up in Nigeria, and I was blessed to have rigor. We had serious math classes in Nigeria. And that's part of what helped me to get to where I am today. And please, we really need to understand what math even is, right? Math is a tool that helps us to understand how the world works. So from the very beginning, in some of these people I'm going to talk about, a lot of them came from a place of believing that there was intelligibility in the universe, that the universe made sense. Dr. Stephen Meyer has written a book called The Return of the God Hypothesis, and he talks about some of the history there. His PhD was in the history and philosophy of science. So before I dive into Isaac Newton, let me just give you the table of contents. This book is called Journey Through Genius. Math goes back to Africa. The numbers from 1 to 9, when we talk about numbers, that's called the Hindu-Arabic system. So I don't know if people don't understand that there's a whole history of mathematics that needs to be understood before we get into some of these conversations that America is having. Like, math is the most universal field ever. It's universal. everywhere in the world, there's some sort of lessons we see from people trying to do math or use math principles. Now, the advancement of calculus and some of these fields of study, yeah, they came out of places like Cambridge and Switzerland and Russia and Germany and Italy and France. But there are institutions of learning in Nigeria and North Africa and different parts of the world that have also produced some things, some key features in math and science. So it's all over. No, I just picked some of the spots because I grew up in Nigeria. So I know for a fact the Yoruba people, how they count, we use that in math history. We see that, right? There's a reason why some people are better at math, by the way, by default, because in their language, 13, for example, is 10 plus 3. So they're learning number sense when they're learning to count. They're learning addition when they learn to count. So language can help you. So I want to encourage you to learn a second language if you don't know any other languages. I speak Hausa, English, and I learned French growing up, but I need to brush up on that. But anyways, here's some of the people in the table of contents. So we have Hippocrates, quadrature. We have Euclid's proof of the Pythagorean theorem. That's from 300 BC. So we see the Greeks there. Euclid and the infinitude of primes. Terence Tao does work with number theory, prime numbers. That's some of that stuff. But notice that this is from the Greeks. Archimedes is discussed in this book. Heron is discussed. Cardano and the solution of the cubic. And now, at this point in math history, we've rolled into the 1600s. So let's start from chapter 7, Journey Through Genius. One of the goals of this is to actually take science in the scientific revolution, and we're highlighting the mathematics involved. So when did the scientific revolution begin? This is going to bring us here to where we need to be. Well, astronomy was part of the basis for that, and the scientific revolution, they would attribute it to around the time of Copernicus, Nicholas Copernicus, the Polish astronomer, and he showed that the sun was the center of the solar system, not the earth. Copernicus lived from 1473 to 1543. In 1450, the printing press was cooking, right, from Johannes Gutenberg. So we get the printing press, and then we get Copernicus, who comes in 1473. Well, he's born then, but notice that he was born at the perfect time to be able to come up with something that can be distributed because the printing press existed. Isn't that interesting? When you're born is important. Malcolm Gladwell talks about this in his work. The best time to be born as a mathematician or scientist was after Newton, because he gave you the tools for calculus, right? So then you have a tool to work with. So let's read a little bit about Isaac Newton and some of the great mathematicians that lived during the scientific revolution. So we are now in the 1500s range. If the 16th century saw a quickened pace of mathematical activity, the 17th century would bring an absolute onslaught of innovation and discovery. It has come to be called the heroic century in the history of mathematics because of the intellectual giants who came and went during these productive years. At this time, the focus of activity shifted northward from the talented Italian algebraists of the previous chapter to an array of the French, German, and British thinkers. There are many discussions about why this happened. Keep in mind that in world history around this time, there's a lot of stuff happening. The Reformation is happening in 1517. So the work of Martin Luther is allowing more people to be able to get access to reading the Bibles. Literacy is growing in Germany, right? So the Reformation, the Copernican Revolution, and the printing press, huge factors in the scientific revolution happening, as well as the age of discovery, of course, happening around this time. So notice 1500, very important time frame right there. Okay, let's continue our discussion. All was not freedom and openness in the North, yet the heritage of the Reformation seemed to favor the kind of unfettered inquiry that would loosen the intellect of a Kepler or Descartes or Newton. It was not mathematics alone that was flourishing as the 16th century became the 17th. In 1607, the British settled at Jamestown. Also, a few years before Jamestown, Galileo had investigated the motion of falling bodies with such care and ingenuity that he forever altered the nature of physics. So Galileo is one of the most we don't talk about him enough. That guy was a boss. Galileo was a boss, and his telescope was wonderful. And of course, Newton made a telescope too. And we see his telescope. Newton comes around 1661 at Cambridge. He was born in 1642. The year Galileo died. So Newton's telescope was impressive. And apparently Newton was just kind of keeping it on the side. And someone says, hey, don't you know that this thing should be shown to the king? And then Newton is like, okay, what's the big deal? Anyways, the king sees it. Newton gets knighted. The rest is history. So we get Galileo. He had investigated falling bodies. 2 years after Jamestown, the same Galileo turned the recently invented spyglass towards the heavens and launched modern astronomy. So we're going to talk more about astronomy. Astronomy gave rise to physics. And physics, some of those applications of trying to figure out certain things in physics, we needed a language, and mathematics gave us the language. So astronomy, physics, mathematics, and chemistry. Chemistry is connected to this because understanding certain things in the universe involves understanding gases and chemistry, right? So chemistry, physics, math, and astronomy should really be friends. 2 years after Jamestown, as we said, he turned the spyglass towards the heavens and launched modern astronomy, even as he simultaneously began the journey that would lead to the personal crisis already mentioned, which was this idea that the church at that time in Italy, the Catholic Church in Italy at that time, had serious concerns about Galileo and Copernicus' work, right? Of showing that the sun was the center. So there was some conflict that happened. So we have Cervantes writing, we have Shakespeare. So obviously culture, this is all happening around 1601. Obviously cultural landmarks do not fit themselves neatly into 100-year intervals, and it was in the later years of the previous century that the first signs appeared of the mathematical revolution that was in store. A heroic century needs heroes, and we shall take a brief look at some of them. In the 1590s, the French mathematician François Viète published his influential In Artem Analyticum Isagoge, which is the analytical art. Viète's approximation of pi was mentioned in chapter 4 of this book, but it is toward developing the symbolic algebra destined to become the alphabet of higher mathematics. Admittedly, Viète's algebraic notation looks far from modern and seems unduly cumbersome and wordy for those accustomed to today's mathematics. So then the author, Dr. William Dunham, gives us an example of this mathematics, which is shown on this page right there. So he made an important step toward the use of letters to designate quantities in equations. Refined and extended in the decades ahead, algebraic symbolism would transform the look and the substance of mathematics in the new century. Early in the 1600s, a pair of mathematicians from the British Isles, John Napier and Henry Briggs, so 1550 to 1617, John Napier, 1561 to 1631, together, that's Henry Briggs, they jointly introduced, perfected, and exploited the logarithm, a concept having tremendous practical and theoretical significance. Logarithms have the remarkable property of simplifying such otherwise tedious computations as multiplication and division and the extraction of roots, so that no scientist of sound mind would thereafter go about finding the seventh root of 234, for example, without the benefit of logarithms. In the next century, Pierre-Simon Laplace would observe that the logarithms of Napier and Briggs he would observe that the logarithms of Napier and Briggs, by shortening the labors, doubled the life of the astronomer. By shortening the labor that they did with their logarithms, doubled the life of an astronomer, right? That's funny. Certainly, the cooperation between Briggs and Napier in this venture is noteworthy and stands in striking contrast to some of the bitter disputes and jealousies that would plague mathematics in the years to come. Unfortunately, Isaac Newton had some problems, some beef, they would say in the hood, with some other people like Robert Hooke and some other scientists of the time. Some of Isaac Newton's concern had to do, I would argue, with saying that someone else took his ideas, like Leibniz, Gottfried Leibniz. Meanwhile, some of those ideas were developed independently in two different regions, right, of the world, Germany and England. Okay, so in math, in algebra, we talk about logarithms, right? And then they introduced Simon Laplace. And Laplace, we talk about Laplace transforms in differential equations. So you begin to see the people behind the ideas, right? And you can try and follow and see, why did they come up with these ideas? So again, we're studying math in the scientific revolution right now. Okay, so the book is going to go on. We're going to continue reading and studying more. We'll get into Newton's story in more detail in the coming videos, but reach out to amos.thestemguy@gmail.com if you want me to update you with that, that particular episode, or you can subscribe to this channel and just stay tuned. We'll be releasing a video regularly about different math and science people. So let's wrap up with a couple more mathematicians. As the century progressed, 3 French mathematicians commanded the spotlight. One was René Descartes from 1596 to 1650. a philosopher and mathematician whose 1637 book, De Corps de la Méthode, became a landmark in the history of philosophy. It was the treatise on universal science that both anticipated and spurred on the great scientific explosion that characterized the times. While the philosophical content of the discourse was widely discussed and hotly debated, it was an appendix titled La Géométrie that most directly influenced the development of mathematics. Did you know that René Descartes' work was read by Isaac Newton, or looked at by Newton, and also by Einstein? So René Descartes laid the groundwork. He died at the age of 54. He used to tutor the Queen of Sweden at like 5 a.m. in the morning. Not a good time to be walking around in Sweden. It's pretty cold. I'm assuming it's certain times of the year. But René Descartes laid the groundwork. We talk about the Cartesian plane in mathematics. When you talk about X and Y coordinates, that's also from René Descartes' work, right? So René Descartes gave us some stuff in philosophy and logic, as well as Cartesian geometry. So let's go back. It says, while the philosophical content of the discourse was widely discussed and hotly debated, it was an appendix titled La Géométrie that mostly influenced the development of mathematics. There, Descartes provided the first published account of what we now call analytic geometry. Like Viète's algebraic notation, Descartes' analytic geometry was far from modern in appearance, but it announced the marriage of algebra and geometry that would become indispensable in the all subsequent mathematical work. If you want to learn geometry and algebra, by the way, in a condensed fashion, algebra 1, algebra 2, geometry, pre-calc, calc, this summer, 2024 summer, or any summer, God willing, as long as we have our online resources, you are welcome to join us. 3 months, you can learn all of Algebra 1 in 3 months. It's going to take some commitment, but it's doable. If you want to get ahead, or if you are behind and you're trying to catch up, you can take the whole algebra course in 3 months, okay? Just something for you to keep in mind. AmosTheSTEMGuy@gmail.com, AmosTheSTEMGuy@gmail.com. You can email me to sign up, and I'll put you on the list. So, we've talked about René Descartes. He gave us the Cartesian plane. Now we have another person. His name, Blaise Pascal. When the discourse appeared, Blaise Pascal, who was born 1623 to 1662, although a youngster of 14, was already attending meetings of senior French mathematicians. He was on the brink of a spectacular, if short, mathematical career. Pascal was a brilliant child, of a kind one sometimes encounters in the history of mathematics. At age 16, he was so impressed the mighty Descartes. He had so impressed the mighty Descartes with his mathematical writings that the latter refused to believe that so young a boy was the author. 2 years later, Pascal invented a calculating machine that stands as the very remote predecessor of the modern computer. Further, he made significant contributions to the theory of probability, thereby pushing the subject beyond the rudiments provided by Cardano a century before. In spite of his obvious talent of mathematics, Pascal devoted most of his adult life to questions of theology, and his work in this area is still regularly studied. A man who often perceived omens in events around him, Pascal concluded that God's plan for him did not include mathematics, and he dropped the subject entirely. I don't like the word omens there, but this is talking about Pascal was spiritual, had a certain sense of, I don't think I'm supposed to do this. Now, he was wrong. That's not the way we should have navigated that, and you'll see why in a second. However, while experiencing a particularly nagging toothache when he was 35, Pascal let his thoughts wander to mathematics, and the pain disappeared. He took this as a heavenly sign and made a quick but intensive return to mathematical research. So, God created the world, and he has given us the opportunity to study the world. So there's nothing wrong with studying the world God has made. We just have to keep the fact that he is the creator, and he's the one that has given us the tools that we have. Think about the intelligibility of the universe. Today I was telling my wife, think about growth. You plant a seed and it grows. The very idea of things growing really points to something about this world that God has made, right? Growth, we take it for granted. But God's evidence is seen all around us. And so if you want to read more on that, I have published a book called Why Do I Exist? And it's free on my website, livingsensibly.org, under the books tab. Livingsensibly.org, Living sensibly.org. And under the books tab, you can see my book. I talk about the existence of God, and I talk about just how to live a life that makes sense. Blaise Pascal believed in God, and he also did his math well. Pascal was also a physicist, so he was a physicist and a mathematician. Pascal returned to mathematical research in an intense manner. Although this lasted barely a week, Pascal managed to discover the fundamental properties of the cycloid curve, a topic discussed in the next chapter. With that, Pascal again abandoned mathematics, and in 1662, at the age of 39, he died. This brings us to perhaps the most remarkable of the triumvirate of Frenchmen who dominated the mathematical landscape in the mid-17th century. The third French mathematician is a man by the name of Pierre de Fermat. Pierre de Fermat. I have a book about Fermat, and if you don't mind, I'm actually going to stand and grab the book here. This is the book. It's called Fermat's Enigma, and it's about Fermat's last theorem. By the way, that idea I told you about doing math in 3 months, there's a whole book here called Rethinking Math Learning, and it actually shows teach your kids 1 year of math in 3 months. So the evidence is out there. Fermat's last theorem comes from Pierre de Fermat, who we're going to talk about. We can't explain Fermat's last theorem in a video. I don't know Fermat's last theorem explanation, like the proof, because that proof took about 250 to 300 years before somebody proved it. And when they proved it, they had to come up with new branches of mathematics to do that. That individual is Sir Andrew Wiles, and he's based out of Oxford University now. But his background is from Cambridge. I believe he grew up in Cambridge, and then he went to Princeton University, got a PhD, and then he solved Fermat's last theorem, which he found when he was a boy, like 9 or 10 years old. And that's why I talk to people about career preparation, even while you're young, because your desires and passions begin to show even from a young age. I used to love paper and math when I was in elementary school. This is a binder here. I want to encourage people to have a binder, and in the binder they should write their interest, and they can explore careers along the way. But this is Fermat from Fermat's last theorem. This is what it says. This brings us to perhaps the most remarkable of the triumvirate of Frenchmen who dominated the mathematical landscape of the mid-17th century. Pierre de Fermat, 1601 to 1665, of Toulouse. Fermat is notable for many areas of mathematics in which he made significant discoveries. He created his own analytic geometry independent of and perhaps earlier than Descartes. And in some ways, Fermat's approach to the topic was more modern than that of his famous contemporary. Of course, Descartes was the first to publish a description of analytical geometry and thereby reaped more of the glory, but Fermat deserves equal credit for its creation. Likewise, a likely correspondence between Pascal and Fermat laid the previously mentioned foundation of probability theory in the 1650s. As if that were not enough, Fermat made great strides toward developing what we now call differential calculus. In some places, France in particular, he is sometimes accorded the honor of being a co-founder of calculus, although most historians of mathematics, while recognizing his achievements, feel that this is going a bit too far. Yeah, I think that's a little too far. Newton and Leibniz, let's leave it there with those guys. And I mean, there's some Indian mathematicians and Chinese mathematicians and mathematicians from the Middle East and so on that did work in calculus and algebra, but we'll get to that later. So we're looking at science in the scientific revolution specifically, but there's actually a whole book on the history of mathematics in general. So we're going to look at that. That's a different course where we're just looking at the history of math. Right now, we're focusing our efforts on science in the scientific revolution. Okay, we're almost done. We'll stop with Fermat. But it was in the area of number theory that Fermat left his most indelible work. We have seen this topic before with the writings of Euclid in his books, book 7 to book 9 of the Elements. We have the book for our students. We have Euclid's book, this Euclid that lived like 300 BC, around the time, 300 years before Jesus. Shortly, we're talking after the days of Daniel in the Old Testament. That's when Euclid comes to the scene. One classic work on this subject was the Arithmetica of Diophantus, who lived around 250 AD. So this is, again, in the area of number theory. When this was rediscovered and translated during the Renaissance, it proved to be a very influential treatise. Fermat acquired a copy, devoured Diophantus' writings, and soon was making profound discoveries of his own about the amazing properties of the whole numbers. It was common for him to state an intriguing result and sometimes claim to have a valid proof, but rarely did he actually provide it. Thus, it was the job of later mathematicians, and more often than not, this meant Euler, to furnish the missing verifications. As a result, mathematics historians are left with the dilemma of determining to whom the credit belonged. To Fermat, who had stated the result and who may have had a proof, or to Euler, who actually wrote down such an argument. By far the most intriguing of Fermat's theorems, the term is used gingerly since so many of his results were stated with an excess of confidence but an absence of proof, was triggered by the work of Diophantus. In his personal copy of Arithmetica, Fermat scribbled a note in the margin beside proposition 2.8, a result about expressing a perfect square as the sum of two other perfect squares. Instances of such decomposition abound. So Pythagoras' theorem, 3 squared plus 4 squared is equal to 5 squared, or 7 squared plus 24 squared is equal to 7 squared plus 24 squared is equal to 25 squared, right? So if we look at Pythagoras' theorem, we can see that it works, right, for squares. And I'm going to write this down here on our board. So 3 squared plus 4 squared is equal to 5 squared, right? That is Pythagoras' theorem. 3 squared plus 4 squared is equal to 5 squared. But did you know that you can't find any two numbers that if you were to raise them to a cube, add them together, they give you the cube of the third number? That doesn't exist. And you can't find any numbers that are raised to the fourth power and you add them together and you get a power raised to the fourth power. That doesn't exist either. And it doesn't exist for anything greater than squares. That is what Fermat's last theorem is about. And this book tells the story and provides some of the guidance for how it was solved. And I long to learn that. That's one of my goals in life, is to master Fermat's last theorem. So Dr. Andrew Wiles, please, if you're watching, you have a student who would love to learn Fermat's last theorem. God willing, I'll be at Cambridge this summer. I was invited and it's paid for me to attend a program at Cambridge, but I might sneak over to Oxford as well. And the idea is I want to understand Fermat's last theorem. So that's what Fermat's last theorem is. And apparently Fermat said that he had a solution, but he didn't have any room in his notes. So in modern parlance, his Jordan's claim that we can never find whole numbers a, b, and c, and an exponent that is the power 3 and above, for which that this is true. If he were correct, then the decomposition of a perfect square into the sum of two perfect squares was really something of a fluke, except for squares, said Fermat. Numbers of a given power cannot be written as the sum of two smaller numbers of that same power. As usual, there was no proof. Fermat attributed this omission merely to the narrow margins of the page of the Diophantus text. If only he had had a blank page to work with, Fermat seemed to say he would gladly have provided the wonderful demonstration he claimed to have discovered. Instead, as with most of his assertions, the task of finding a proof was left to posterity. In this case, posterity is still looking, for Fermat's assertion remains to this day unsolved. Let's pause. This book I'm reading to you was written, there's an actual problem I didn't realize. This book was written in 1990. And let's pause. Because in about 1994, Sir Andrew Wiles solved Fermat's last theorem. So in this case, posterity is still looking. The author says, yeah, but I'm sorry, this book is actually outdated, but the stories are still cool, except this one with Fermat's last theorem, which has changed. Even Euler, who unraveled the mysteries of so many of Fermat's theorems, could prove the assertion only for n is equal to 3 and n is equal to 4. That is, Euler showed that indeed a cube cannot be written as the sum of two cubes, nor a fourth power as the sum of two fourth powers. We're going to study some Euler. I have his book here. We're going to study Euler's Elements of Algebra. We're going to do some work with Euler's book. So stay tuned for that class where we go over his book, and maybe we'll find some notes on this. But resolution of the general case, today popularly known as Fermat's last theorem, is still anyone's guess. The betting odds seem to be that Fermat was correct in this, as in many other of his unproved assertions. Nonetheless, no number theorist to date has managed to prove the result true, except Dr. Andrew Wiles, who has done that now. Nor has anyone cooked up a counterexample to show it false. In this sense, then, calling it his last theorem is surely a bit premature. Should anyone resolve the issue, and even in the late 20th century, interest in the problem runs high, he or she will surely merit a page in all subsequent histories of mathematics. And that's how Andrew Wiles now is very famous for his work in this, right? Like he won some awards and many people know about him. And so if we were somehow to return to the summer of 1661 and survey the mathematical legacy of the 17th century, we would have so much of significance to behold. Algebraic notation, logarithms, analytic geometry, probability, and the theory of numbers all had come into their own, and the names of Viète, Napier, Descartes, Pascal, and Fermat would be justly revered. They were heroes indeed. Of course, no one on that summer's day would have paid the least attention to the quiet beginning of a mathematical journey that would soon eclipse them all. The journey was to commence at the beautiful Trinity College of Cambridge University in the summer of 1661. A young lad from nearby Woolsthorpe was about to begin his university career. He had previously shown promise, but much the same might have been said about the dozen or so equally obscure classmates with whom he began his Trinity experience. But this lad was on his way to become the supreme hero of the heroic century and simultaneously to change the way mankind would ever look at the world. His name, of course, was Sir Isaac Newton. Back then, it was just Isaac Newton. God willing, this summer, I'll be out at Cambridge University at Trinity College, and I look forward to studying the work of Isaac Newton. Stay tuned for our next video and subscribe for more.